Hello, good morning and good afternoon, whatever time is right now. Before proceeding, let me introduce myself. I am Chanchal Singh from MTech Photonics. This PPT is submitted to Maya Goswami sir. My topic molecular dynamics simulation. It is a great tool to study the properties of material and to see how molecules move at atomic level. This is a powerful tool used to predict the material property, to design drugs and biomolecule and much more. It is basically an experiment inside the computer. It is usually used when real world experiments are too expensive and too time consuming. Suppose we want to know the properties of new material before actual making it in the lab. This can be done by running molecular dynamics simulation. It is economical and fast process. Now go further. Let's talk about some history. First molecular dynamics simulation was done in 1957 to study the properties of hard sphere fluid. As compared to molecular dynamics simulation today, they had relatively small number of particles in their simulation box. But now it contains complex and large number of particles because we have access to more powerful hardware. To run molecular dynamics simulation, we're having a three-step. First, create an initial state to introduce interaction potential, predict how particles move through Newton's equation motion. Initial state. To create initial state of a system, we need to define the initial position and the type of particle. It can be done either manually for simple system, or we might need to make use of current existing tool to create our initial state for more complex system. Here you can see I initialize the particle in x and y coordinates. This is the position which I initialized in simulation box. Interaction potential. To introduce interaction potential of our system, we can use existing so-called forces field. These forces field mathematically formulated that describe the interaction between particles. They are developed by academic group around the world and are well tested in which makes our life much easier for molecular dynamics simulation. We see some example of such forces field: bonded, unbonded, and external field. Third step, Newton's equation. Newton equation, this is also force equation, which is nothing as mass into acceleration. Here you can see m, this is nothing as it is acceleration, equals to force with change with respect to time. In practical, Newton's equation are usually used instead of Hamiltonian formula. Molecular equation of motion, force into acceleration, in different form is given by dv over dr equals to m, and d over dr, this is nothing else, this is acceleration. In md simulation, Newton's equation is integration to get the coordinates r at time t, given the initial coordinates r naught at time t naught. There are different integration methods such as the Verlet integrator. Before this, I show if the particle at the initial position there is no changes, it is in their fixed position. If we change some parameter, for example, if we change the temperature, we see some disturbance creating in the position of the particle. Verlet integration. Verlet integration is a numerical method used to integrate Newton's equation of motion. It is frequently used to calculate trajectory of particle in molecular dynamics simulation and computer graphic. The Verlet algorithm uses position and acceleration at time t and the position from time t change to calculate the new position at time t with respect to new time. This is MD flow. MD, यार मैं MD flows. So the flow of typical molecule simulation is follow first initialize the system, then computing force each other in the system is done based on the integration. अरे यार. So the flow of typical molecule dynamic simulation is follow the first initialize the state. अरे यार. So the flow of typical molecular dynamics simulation is follow the first initialized the system, then computing force on each particle in the system. This is done based on the interaction potential between particles. After that, calculate new particle position and velocity of a particle based on the force exist on each other and adjust properties on other parameters. Here you can see if we change some parameters how it behaves. Periodic boundary condition in total. If we have a large nearly homogeneous system, example liquid or solid, we can stimulate a small chunk of it, the center box, and then assume this chunk is repeated to infinite in all directions. This drastically reduces the number of atoms we need to consider explicitly. A molecule move out of the central box, come back in opposite side. The direction cutoff can be used to resist interaction to just the center box and its nearest neighbor box, assuming the central box is a large enough. I'm going to write my molecular dynamic code now. Before this, this is a flow chart. First, we start initial position. I gave the initial position code to define the initial position of the particle. Then we make some changing in the parameters, for example, in temperature, in velocities, in kinetic energy. Then we see the new position of particle. Here, the initial position of the atom or molecule in a system in this way. It is the initial position of a particle in the system. This is a position when we add some perturbation. Perturbation may be adding some temperature, adding change in velocity and some parameters. You can see change in position of atom. So now this is a code for initial particle position. Here are some parameters where I wrote this code. This is n particle, which is 100. It is a number of particle. Box size equals to 100. It is the size of stimulation box. It is the initial position of a random particles in 3D in box size, which covers the whole box. This is some XYZ and labeling the, you can see, and directly you can copy this code on the MATLAB. You can see this is the uh, this is result. There is no change in parameters. It is a initial position, which is fixed position in the box. This is my second code. This is actually my molecular dynamics simulation code, where you can see the change in molecular dynamics, which means after changing in velocity, in temperature, in kinematics, you see the new position of the particle with respect to time and change in velocities. You can see here I give the loop for stepping up, and you can see velocity, it is an initial velocity and this is a new velocity with change in time. It is a previous position and this is a new position change with velocity and time. You this is also, it is a kinetic energy, zero point 0.5. This is a mass. This is the sum of velocity. You this is a current, is a scale, and you can just copy and paste on MATLAB. You can see the result. This is how the particle move. You can see this after giving some perturbation, after giving some change in parameter. This is see how molecular dynamics simulation see. This is a reference from where I study this material. You can go through this. Thank you so much patiently listen to me. Thank you so much.